to put this plain, simple English description into an equation, I will then rewrite the equation, and I'm going to do a little bit of algebra here, and hope you can bear with me on that. I'm going to put all of this on one side of the equation. And then I'm going to fill in this term here that will represent the rate of increase within my control wall. So the first step is I algebraically fold all the term onto one side, and then I have that equal to 0. The mass flow out become positive, the mass flow in become negative. This is just for convenience, and I'm doing that for sole purpose of using this as a springboard to discuss the momentum equation. So the mathematical formulation for the so-called rate of increase of the mass in my control volume can be represented by as follows. I will integrate my density in this volume. So I have a tiny cube within this space of the control volume, which is represented by differential volume of dx dy dc. So this is differential volume calculus. And that differential volume has a density within that tiny differential space. I'm going to integrate that all over my control volume. And when you do that, what is that physically represent? In plain, simple English. I take the density, the mass, very good. This is the mass. All right, so I have the mass here in my mathematical formulation. And what I want is not the mass, what I want is the rate, time derivative. So this whole thing has to be differentiated with respect to time. Do you see it? So if I were to put this equation, I'm just recopying the layman simplest physical description of the continuity equation. I'm just rewriting the description about with the appropriate sign. So I have the first term, which is the rate of, this is very confusing. I'm going to take away the mass because it's no longer what I'm representing. I'm looking at the whole term here. The first term to be read in plain, simple English is the rate of increase, rate of increase of mass in my control volume. That, for an unsteady problem, must be balanced by the mass flow rate out minus the mass flow rate in. That's fluid mechanics. That's the simplest formulation of the continuity equation. And I will put here a sign to remind you that you need to be careful to keep the sign. And then we're going to build on this and still keep adding other spice. So right now I added is the unsteady aspect, which in some of the homework you will have to deal with. All right? Any question before I continue? Okay, now, with that, let me touch on the second homework, 12. And then with that, I can modify that equation for more relevant type engineering problem. So 5.12, again, I don't want you to copy, but just listen. It's a cooling tower. Cooling tower in a power plant can be fossil fuel power plant or nuclear power plant. The problem is you have hot water from the condenser that you cannot dump into a river or lake. Why is that? So you have 100 degrees Fahrenheit water that you have to put somewhere. Why not just flow into the street or dump into a lake?
To enrich the ecosystem?
Yep, you kill all the fish. Right? So you have to further cool it. And the problem statement is I have water at 110 degrees Fahrenheit, which is warm. Somehow I have to cool it to what? 80 degrees Fahrenheit, so that now I can pass it on to the river. And that happened in the New River and any other places. And the way it can be done is you add dry air. Why would dry air help cool the water out? So you like them to mix this wet 110 degree water, warm water, mix it with air, yes.
Takes like the vapor out of it more readily.
You help the water to evaporate. So the evaporation will cool the water. And that's why you want to add dry air for the sole purpose of evaporation. When the water evaporates, it cools. And that's how you achieve 80 degrees from 110 degrees. So the schematic of which this can be achieved is a tall tower. There are multiple inlet and exit because you have water and air, and then you have mixture of water and air and cold water. Actually, 4 different streams as shown in here. And here's your control arm. And let me label the different entry and start setting up the problem for you. So I have 4 stations, 1, 2, 3, 4. And at the bottom entry on 3 is dry air. All right? You were told in the problem statement how many pound mass per hour of dry air coming in at the base. Where do you think the warm water will be coming in from the other 3 ports that will make engineering sense? 1. Yeah. Yeah. Why? Because then the warm water will have more chance of being mixed with the dry air, and all the turbulence will help promote evaporation. So this is where the warm water will come in. And again, you were told how many pound mass per hour of flow coming in. So this is 110 here. What about the remaining 2 ports? What do you think is coming out from 4?
Cool there. Oh, sorry. Cold water.
Cold air or cold water?
Cold water.
Cold water. Water. Yeah. This is where you dump to the river. So this is 80 degrees, and this m.4 of cold air, cold water, sorry, is what one of the questions that the problem statement asks. Okay? Are you on top? Understand the problem? What is being asked? So what's coming out from the chimney? That sometimes you see a haystack of white smoke, and somehow yeah, it's just a mixture of air plus water. All right? And you were told how much of that too. Do you understand the problem statement? So what is being asked in addition to the cold water dumping into the river is that how much water, I call it m.2 of the water that is evaporated, mixed with the air. So this is basically the problem statement. It looks kind of daunting and it's very unconventional because of one single reason. Because you have two fluids, air and water. How many times you think you have to apply the continuity equation? Twice. That's it. That's the tip. Yes?
So does continuity apply for like the same, like, I guess, it only applies for air and then only applies for water, like you can use it in two separate?
Correct. Yeah, in this case, you do have to keep it separate. Air is air, whatever come in here has to be accounted for, right? And all has to go out where? This mass flow of air. There's only one place it will appear. Right? So that's the hint. Yes?
So you can make the assumption in this problem that all of the air coming in leaves the top.
Yes, correct. And it's steady without any ambiguity, unless your toe is not steady, it's always steady. Yes?
As the temperature of the air changes, shouldn't the density change also?
We don't assume density changing in any problem unless, again, you're told otherwise. Yeah. So steady and incompressible are a given assumption unless you are told, or the problem is such that it's obvious, which is the next one. Yes?
So water comes in there, out there, but it's also coming out the top, so when we're doing the continuity for them, do we include the top?
Yes. The question for those in the back is, I have water coming here, I have water leaving here, but also water going out. Okay? So you need to both keep them all together. Does that make sense? Right? Is that what you're asking? Answer is yes. Yeah. Air, water. Mm-hmm.
So would we do like the sum of the mass flow rates on one side for water? And then like when we're using the continuity equation, we would have like, I guess like m dot 1 equals m dot 2 plus m dot 4.
So I know what you're asking, but I don't want to answer it. I mean, you only given 1 minute. So go home, open a bottle of wine, or beer, whatever, at home. Okay, so what's the point of doing this now is to tell you in some problem, I don't have the simple one port in, one port out. And there may be multiple entry. So to be more general, I like to throw in a summation sign. Just to account for multiple entry and multiple exit. Nothing big, but enough to alter the equation. Right? Questions? So there was a question about density, or perhaps with this summation sign, I want to touch on, so I'm giving you a hint on 12, let me touch on 17, which relate to this summation sign. So 17 will be a pipe, circular pipe, that is annulus. In the center of this pipe, I have another pipe that I call station 1. This center pipe has a stream of water that is streaming down this pipe. There's water everywhere, within this first pipe, within this second pipe. So I have a high speed of water coming down this center tube, which is the shaded area. Yes?
Does the center tube go all the way through the other pipe, or is it?
No, it ends in here.
Okay.
Right, it's just a high jet of water flowing down from left to right around the center tube. When you have a high-speed fluid like this, it creates a suction, a vacuum. And we'll examine that by way of Bernoulli in maybe a month. So high velocity creates low pressure. And what happened then is the periphery water on the outside get entrained or pumped or get sucked in into this annulus. This is called a ejector. Ejector because of this high velocity center jet. Pump. Pump because without any moving part, it is pumping water. And it's used in a lot of processing chemical plant where they have excess of steam, for example, for other processes, and they will want the steam, very high energy, couple of thousand PSI, 2,000, 3,000 degree Fahrenheit, and they just run their screaming jet down here, and the high velocity steam will create a suction that can draw air in and use as an air pump. Right? So that's more in the future, but right now, what you are asked is for this given inlet station, and you have to decide whether to draw the control water. And if I go much, much further downstream, the flow exiting, and again, I don't want you to copy, will all be mixed, so there's a lot of turbulence in here. And the flow mixes out and come with one uniform velocity jet. And all those area and velocity given, you're asked how much pumping, QQ. What is the volume flow rate of all this suction due to this high velocity jet? Do you understand the problem statement? Very simple. The only caveat is now you have to consider multiple entry. So summation in now have more than one port. And the exit, you have to consider how to deal with that for the out mass flow rate. Other than that, it's not difficult. Questions?
Yeah, is the water in the larger tube independently pumped, or is it pumped because of the inner tube?
The water from the outside, if I may draw that better, may coming out from a separate reservoir. So how much is being pumped is solely a function of what is in this jet. The faster, more entrainment. But that is not the purpose of this problem. This is strictly an application of continuity. Velocity is given, area is given, you know what to do, right? And the only twist is the area is a little awkward at station 1. You have to account for that, and the fact that you have more than one entry port, and hence the summation sign will be needed. Okay, other questions on this problem? To further alter this continuity equation, I need to revisit your homework due today. And I put it in the center here. And that has to do with what I call direction cosine, which is this item. So for that, let's revisit the garage problem. So here I will draw the control volume. And this is going to take a little time to get everything settled. And I want to make a little change from your homework problem in that I want to actually use a different angle. Theta. For what I wanted to modify this continuity equation so that I can account for the case where the velocity and the area is not perpendicular. All right, because this formulation assumes that they're all perpendicular. And I will use this homework problem with the twist that the inlet velocity at the garage door, the angle now is theta. Still different from what you have done in your homework. So the way you can account for that, and you have seen it in the homework problem, is when I draw a control volume, I'm going to now define some unit vectors. And with the overhead. It's what I call the unit outward normal. So when I have a control volume, that normal is always pointing away, outward from my control volume. And when I have a velocity, which is a vector, v, the angle between the velocity and that outward normal is what I call theta. So the garage problem is one specific example of how this general formulation can be used. So let me just bracket that off. I'm going to use this diagram to modify my continuity equation to allow for so-called directional cosine, which is the fact velocity and area may not be perpendicular to each other. So I want to give you three extreme cases where I use the word out, meaning theta is 0 degree. So here's my diagram. Here's my control volume. Velocity. Theta 0, meaning pointing straightly parallel to the outward normal. What you give that for the velocity here is rho VA cosine theta, right? Because area perpendicular to the velocity. Area is A, velocity is V cosine theta, right? So this is what I meant by directional cosine. And that is represented by rho V dot N times the area A. Have you seen this dot product before from calculus? Dot V and N, meaning that I'm interested in the cosine in the velocity and this outward normal. So I have now a nomenclature that involves